Materials, question 2. Part A. State what is meant by the strength of a material. Well, strength is the ability of a material, regardless of its dimensions, to withstand a force without breaking. Part B. Describe the behavior of a brittle material. Well, a brittle material will break with little or no deformation. Part C. Sketch a stress-strain graph for copper up to the point at which it breaks. Well, stress in pascals goes on the y-axis, with strain, which has no units, on the x-axis. Copper would have an elastic region here, with a straight line. It then undergoes plastic deformation with a large strain from no increase in stress, and eventually it would break around this point. Part D. Label the limit of proportionality with a P, the elastic limit with an E, and the yield point with a Y. Well, the limit of proportionality is where the line is no longer linear, around about here. Soon after that we reach the elastic limit, beyond which the wire would not return to its original length. The yield point is where we get a large amount of plastic deformation at this point. Part E. What word describes materials that behave like copper when under tension? Well, copper is a ductile material. Part F. A 120 cm long copper wire of diameter 0.6 mm supports a mass of 400 grams. If copper has a Young modulus of 120 gigapascals, calculate the extension of the wire. Well, from the data sheet we know that the Young modulus E is equal to the stress sigma divided by the strain epsilon. But stress is given by force divided by cross-sectional area, and strain is change in length over original length. We can write this as Young modulus is equal to FL over A delta L, because here we're dividing by a fraction, and what we can do is multiply by the inverse of the fraction. We can rearrange for delta L as force multiplied by original length divided by the Young modulus and the cross-sectional area. Force is given by mass multiplied by gravitational field strength, which in this case 400 grams is 0.4 kilograms, multiplied by the gravitational field strength of 9.81 newtons per kilogram. The area of the wire is given by pi d squared over 4, and that is pi multiplied by 0.6 times 10 to the minus 3 meters, because we were given the diameter in millimeters, all squared, divided by 4. So we're now ready to put all our data into this equation, which I'll do down here. The 4 I'll come back to in a moment. The force is given by this term. The length we were given in the equation as 120 centimeters, so I've put it down as 1.20 meters. The Young modulus is 120 gigapascals, or 120 times 10 to the 9 pascals, and the area given by this term, as we're dividing by a fraction, I've inverted the fraction, which gives the 4 up here, and the pi times 0.6 times 10 to the minus 3 meters, all squared, appears down here. Doing this calculation gives a change in length of 1.4 times 10 to the minus 4 meters. Doing everything in one final calculation like this saves time and also prevents rounding errors, as all the numbers are placed in your calculator at once. However, some of you may not be confident in tackling a calculation like this and will prefer to do things in stages. So now I'm going to go through the same calculation, but in stages. The force is given by mass times gravitational field strength, and here I've completed the calculation at 3.924 newtons. The area of the wire, given by pi d squared over 4, which I've now calculated as 2.83 times 10 to the minus 7 square meters. Now, putting my data into this equation is a little easier. I've got the change in length is equal to the force of 3.924 newtons multiplied by the length of 1.20 meters divided by the Young modulus of 120 times 10 to the 9 pascals and the area of 2.83 times 10 to the minus 7 square meters. In this case, I get the same answer as before to one decimal place at 1.4 times 10 to the minus 4 meters.